In this video, I'm going to explain you the structure of Mifare Ultralight EV1. Mifare Ultralight EV1 is manufactured by NXP Semiconductors, and this is very similar to the very successful Mifare Ultralight cards. So as you can see here, the documentation says the Mifare Ultralight EV1 is succeeding the Mifare Ultralight ticketing. So the first question is, where do we buy this Mifare Ultralight EV1? It is very difficult to find this card on internet. However, there's one particular site where I buy most of my RFID cards. So that is the Rapid NFC. So as you can see here, so this version of Ultralight supports version Ultralight EV1. So when you go to this page, don't forget to select this option. If you don't select that, you'll end up getting an ordinary Mifare Ultralight. So the Ultralight EV1, cost wise, this is around 38 pence in UK. So you also got one more variant that's kind of a metal disc. So this also is EV1 Ultralight, and this costs you around 70 pence, as you can see here. Probably by the time you buy, the price would be cheaper as well. So here, this is a key fob, and this also Mifare Ultralight EV1, and which you can buy for 40 pence. So in order to understand the structure of this particular NFC tag, it's always better you read the original documentation. As you can see here, if you go on Google and type Mifare Ultralight EV1, you can find this PDF. So we just have to go through this paragraph by paragraph, and I try to understand what it is. From programming point of view, you don't have to go into the electronics of this particular chip. So I'm going to just walk you through some of the important paragraphs here. So I'm just going to start scrolling, and I'm going to stop when the things are important for us. So as you can see here in this the security section, you can see that it has got a 7-byte UID, and it has got 32-bit OTP. That's a one-time programmable area. This is something, this feature we can use it as a limited entry ticketing system. And interesting thing, it has got 3 independent counters. So if you have read the other NTAG tags from Mifare, most of the other tags have got only 1 counter, whereas this has got 3 counters. Again, we just don't know why it is. Probably you can find some application where the 3 counters are required. So it provides locking the pages. It supports ECC based originality signature. This feature is available in NTAG 210, 212, 213. Looks like the NXP has brought some features of those cards into this Ultralight EV1. So an ordinary Ultralight never had any password protection, whereas this particular version has got a 32-bit password protection. Again, if you have read the documentation on NTAG 210, 213 or 215, you can see that they all have 32-bit protection. Okay, and looks like there are 2 different variations of this. So looks like you can buy one with say 384 bytes user memory, or you can buy the one with say the more than that 1024 memory bits. And again, as you can see here, so there are 2 versions, one with the 20 pages and other one with 41 pages. So this section summarizes some of the important features. I've just highlighted what is important from the programming point of view. And some of the applications are, it's a public transportation or loyalty cards or event ticketing. So I've done a couple of projects on event ticketing, and I have used this Ultralight EV1. So this is more of electronics, and we don't need to worry about them unless you're designing antenna. So again here the block diagram is the same information what you already know. So this one, as I said, it's not very important, but it's a flowchart how this tag works with any RFID like PN532 or MFC522. So it's just this in fact is not very important from program's point of view, because we always try to use a library provided by the manufacturer, or could be some kind of open source libraries. So in fact the entire document is written in a very simple sentences. I'm sure if you read them you'll understand. So the one of the important thing I just remembered is there's something called the authenticated state as well, because this card supports password. So once you authenticate, once your password is right, this card will be in an authenticated state. Then this allows you to access some of the protected memories, which I'm going to explain in detail, how to protect the pages. Yeah, this is something more important for a programmer. So this is the block diagram of the memory structure. Any RFID or NTAG, eventually they do have some kind of a memory, and which is protected, and it also carries some kind of an ID, as you can see here. So the memory is organized into pages, and each page is the 4 bytes of memory. So the page 0 and page 1, as you can see here, they got the serial number, and after that you got the log bytes, and after that page 4 has got the OTP, and from page 5 onwards up to page 15 you have got the user memory. So this memory is like any other memory, you can write whatever we like. Following that is the configuration. This is something which is not present in the ordinary ultralight. So configuration 0, configuration 1. So looks like there are 2 configuration pages available, followed by the password, where the page number 18 stores the password, and after that you got a pack, and after that you got 3 counters. These are one-way counters, you can just increment them, but you can't decrement them. So if you compare this diagram with an ordinary ultralight, you will realize that the top section, the first 0 to 15, is identical, and after that from page 16 onward, these are something very similar to what you find in NTAG 210 or 213. Following this you got a very similar structure. As I mentioned before, I've never seen the higher version of EV1. So what I have to show you today is also based on this version with only 16 bytes of 16 pages of data. So the only difference between this and the previous one is the amount of user memory. So if you understand the structure of the first one, probably you're also through with the second one as well. And following this shows how exactly the 7-byte UID is stored. It's good to know the bytes where the data is stored. Again, you cannot change the UID. They're all hard coded during the manufacturing time, so you have to keep that in mind. So as I can say, as I mentioned you, the pages can be locked. So this diagram explains how the lock bits work. So there are 2 bytes for locking purpose, and so the lock byte 0 controls locking the page 7, locking page 6, locking 5 and 4 OTP, and the lock byte 1 can be used to lock the pages 8, 9, 10 and 15. And there's something called the BL. This is like the locking the lock page itself, which I'm going to explain. You'll understand that better. And the Logbirds 2 and Logbirds 4, this is used only with the higher version of this card, which has got more memory. So here each bit they'll lock 2 pages. Okay, so as you can see here, so the 0th page byte, so for example, if the bit 7 is set to 1, so this locks page number 30 and 31. So one bit here controls locking of 2 pages. So you have to bear in mind, all the locking is like a one-way ticket. So once you lock a page, you can never unlock it. So this, like, like a write one step of memory card. So the OTP is one-time programmable. So you got 4 bytes of OTPs, which gives you 32-bit. And again, this is all one-time programmer. Once you set the bit to 1, you cannot undo it. So you can use this feature to create a 32 entry ticket system or an event system. And the next is about the data pages. This is where all the read write goes. And the next is the configuration pages.